All right, so for this problem, we're given that we are doing a tensile test on a steel rod. It gives us the data that the force applied to the rod is 102 kilonewtons. It initially had a diameter of 25 millimeters. It now has a diameter of 24.9 millimeters. It had an initial length of 100 millimeters and is now stretched out to 100.1 millimeters. And then it asks us to find Young's modulus, which is also known as the modulus of elasticity. All right, so Young's modulus is defined as stress divided by strain in the elastic region for our material, right? So that means we need to calculate both the stress and the strain for this object. So we'll do strain first, since that's a little easier. So strain is equal to change in length divided by initial length, and we're going to use the same trick where we just say that's now the final length minus the initial length all over the initial length. Gives us 100.1 millimeters minus 100 millimeters all over 100 millimeters. Gives us a nice unitless 0.001 for our strain. All right, so next up is our stress. So stress is equal to force divided by area. So the force is pretty easy. They gave it to us as 102 kilonewtons. However, for the area, they gave us diameters. So we need to figure out what the area of our rod is based on the diameter, right? So the base equation for that is that area of a circle is equal to pi times the radius squared, which is equivalent to saying it's pi times the diameter squared over 4. Right, so that's the version I'm going to use because they gave us diameters. So pi times d squared over 4. Well, so now the question is, do we use the initial diameter of the rod, or do we use the current diameter of the rod? So this is where we get into how stress and strain are actually calculated in engineering applications. So when we calculate strain, we use this difference between current length and initial length. When we calculate stress, the diameter of our object is constantly going to be changing as we apply more and more force. So if we were to use that constantly changing area, our stress would be calculated by a constantly changing force as we apply more and more force, as well as a constantly changing area. So we'd be varying both things in that relationship that calculates stress. So instead, the way we do it in engineering is this area on the bottom for stress is always the initial area, right? And so in that case, we're going to be using the initial diameter, that 25 millimeters for this calculation. And that's going to be true for this whole class. So we have 4 times 102 kilonewtons over pi times 25.0 millimeters squared. Now we've got a couple different unit conversions that we need to take care of here. So first of all, kilonewtons, we want to go back to the base unit of just newtons. So 1 kilonewton is 1,000 newtons. And then we also want to go from 1,000 millimeters is 1 meter, and it's millimeters squared on the bottom, so this term will have to be squared as well. So at that point, we'd have kilonewtons canceling kilonewtons, millimeters canceling millimeters, and we would be left with newtons per meter squared. And a newton per meter squared is also known as a Pascal. So we plug all that in, and we get that the stress in the bar, or in the rod, is 2.078 times 10 to the 8th pascals. Now you could go ahead and use some metric prefixes here. However, we still have one more calculation to go, so I would just leave it in the base units of pascals, get the calculations done, and then we'll figure out what the most appropriate metric prefix is. So we have our stress of 2.078 times 10 to the 8th pascals divided by 0.001. Plug that in and we get 2.078 times 10 to the 11th pascals. So at that point, we have to decide which metric prefix to use, because using scientific notation for our answer doesn't tell us as much useful information. So we know that times 10 to the third is kilo, times 10 to the sixth is mega, times 10 to the ninth is giga. So it looks like giga is going to be most appropriate for us. So we have 1 times 10 to the ninth pascals is 1 gigapascal. So that's going to be 207.8 gigapascals. And just for you going forward through this class, that is about the order of magnitude that you should expect Young's modulus to come in when you're talking about the metric system. When you're talking about the metric system, you should be looking at between the tens and hundreds of gigapascals. When you're talking about the English system, you should be talking about tens or hundreds times 10 to the sixth psi, right? So a common one that we end up using is for ASTM A514 steel cable. The Young's modulus ends up being 29.0 times 10 to the sixth psi. And if you were to go convert back from metric to English, you would see that those two numbers are of the same order of magnitude. So again, when you're talking about Young's modulus, the numbers you should be getting are in the tens or hundreds of gigapascals, or in English units, tens times 10 to the sixth psi.